Hello, my name is Alex Triano, and I am an engineer within the solid-state relay team at Texas Instruments. Thank you so much for joining me today for this webinar. We will discuss how to enable better reliability in hybrid electric vehicles and electric vehicles with best-in-class isolation technology. Let's start by taking a look at where isolated switches are used in EVs. There is an overall market trend towards adopting higher voltage battery packs, and as a result, there is an increasing need for isolated switches throughout a vehicle. For example, when a system or vehicle is first turned on, there is a need to pre-charge high voltage capacitors within the battery management system. Similarly, when a vehicle is turned off, any HV capacitors must be safely discharged in systems such as traction inverters or onboard chargers. Now, during operation of the vehicle, frequent monitoring of high voltage rails is done within the battery management system, and in particular, insulation resistance is monitored in order to ensure that high voltage is separated from the metal chassis ground. In each of these cases, a reliable isolation solution is needed. Now, let's take a look at some of the isolation technologies that are available for these switches. On the left, you'll see electromechanical relays. These devices often use air or a specific mixture of gas as their dielectric material. The strength may be in the range of 1 to 20 volts RMS per micron, which means as a result, these solutions need to be physically large in order to achieve sufficient isolation for high voltage. The benefit of these relays is primarily the low on resistance achieved, since they essentially create a metal-on-metal connection. The trade-off is the associated speed and wear out because they are mechanically based. It can take milliseconds to turn on or off, and you need to stay within design limits for things like vibration or magnetic immunity. Most relays specify operation temp up to 85 C, and they are often an expensive solution to adopt because of the cost of materials and assembly. Now, photo or optical-based isolation use higher dielectric materials. They offer strong EMI performance, but a trade-off is they can also wear out over time as the LEDs can suffer from photo degradation or partial discharge failure. Because light energy is limited in these small devices, there is a limited amount of power transferred. Most photo relays are rated up to 85 C operation. Now, one of the isolation technologies we use at Texas Instruments is an inductive transformer. A laminate or polyimide material is used, which offers a high dielectric strength. High speed and high levels of power transfer can also be achieved. One trade-off is the need to design the IC to limit EMI emissions. Techniques such as Faraday shields or spread spectrum modulation are used in order to ensure EMI performance meets automotive standards. These transformers can operate at high temperatures such as 125 C and are cost effective. Another isolation technology we use in our solid-state relays is capacitive isolation. This uses silicon dioxide, which offers the highest dielectric strength. High speed and low power consumption can be achieved. EMI emissions must be limited within IC development, and overall, capacitive transfer of power is limited. In summary, TI's inductive and capacitive isolation technologies provide the highest dielectric strength at the fastest speed, highest operating temp, and lowest cost. These technologies are used in TI's isolated switches and drivers to form a complete isolated solid-state relay solution. They offer increased reliability with no wear over time since there are no moving parts. Now let's take a look at how these solid-state relays function in an application. We will start with precharging high-voltage capacitors. When a system is first turned on, there are HV positive and negative contactors which connect to a high-voltage DC link capacitor. Failure to manage inrush current will result in damage such as pitting or welding of the mechanical high-voltage contactors. A solution is to use a pre-charge circuit along with a power resistor to limit current during startup. The TPSI 3050 Q1 and TPSI 3052 Q1 are isolated switch drivers which form a solid-state relay solution for this pre-charge switch. They offer 5 kV RMS reinforced isolation, are automotive qualified up to 125C, and integrate their own isolated bias supply. They can drive different types of external switches, such as silicon-controlled rectifiers, MOSFETs, IGBTs, or silicon carbide FETs. Options are available for 10-volt or 15-volt gate drive, so you can optimize for solution cost versus efficiency. The solution size can be up to 80% smaller than a mechanical contactor. The second application is active discharge. When a vehicle turns off, or in the case of an emergency crash, there is a need to discharge high voltage capacitors to a safe level within seconds. Solid-state relays can be used to perform this function and connect or disconnect a high-power pull-down resistor. This can typically take anywhere from 2 to 4 components as shown on the right, as an isolated power path and isolated signal path would be needed. Now, using TPSI 3050 Q1 or TPSI 3052 Q1, this same functionality can be achieved with one IC, leading to a smaller solution size. Once again, these switch drivers are now available on TI.com and offer a great solution for active discharge within a 400 volt or 800 volt system. The last application we will discuss is insulation resistance monitoring, which is done within a battery management system and other subsystems such as onboard chargers. The problem is that high voltage battery terminals must be insulated from the chassis of the vehicle in order to protect drivers and passengers. High voltage isolated switches SW1 and SW2 are used to connect known resistor values, R1 through R3, and calculate the unknown insulation resistance, R-ISO-P and R-ISO-N. The TPSI 2140 Q1 is a solid-state relay designed for this application. It is a 1,400 volt, 50 milliamp isolated switch with over 26-year projected lifetime and an isolation rating of 3.75 kV RMS. It is automotive qualified up to 125C and is suitable for both 400 volt or 800 volt battery systems. It offers 2 milliamps avalanche capability, which means it can survive stress tests done such as high pot or high potential tests and surge tests up to 4 kV without the need for external components like a reed relay disconnect. They enable use of less than 1 mega ohm high voltage resistors, which leads to improved accuracy and safety of these high voltage measurements in the battery management system. In summary, isolated switches are used throughout EVs to solve problems including pre-charge of high voltage capacitors, active discharge, insulation resistance monitoring, and more. TI's new portfolio of solid-state relays use both inductive and capacitive isolation. They use high dielectric strength materials, which help reduce solution size and cost. They are qualified up to 125C and offer robust isolation barriers with over 26 years of projected lifetime. They offer size, reliability, and cost advantages over other technologies such as mechanical relays and photo or optical relays. Thank you so much for your time today. If you would like to learn more, visit ti.com/SSR. Thank you.